So on number 17, they said write an equation for the speed. Well, we have an equation for the speed. Now, what we've done up till now is we've said find the speed at a certain time, right, at a certain instance. But now it says find a formula for the speed in those equations, which is the same problem we did yesterday, right? So it was, so what we have here is we had x of t was what, 150 t, and x and y of t was 7 minus 16t squared. Isn't that what they said there? 17. So the speed would be square root, what's x prime? 150. What's y prime? Negative 32t squared. So right there. So that would be 17c. Right? I mean, I think sometimes in these parametrics, and I said this the other day, we make it a lot harder than it really is. It's just that find an equation for the speed, right? So x prime squared, y prime squared, and then you could graph that. Then you could just get on your calculator and you could just graph it, I think is what they wanted. So it said find a formula for the ball speed, plot this over an appropriate interval, because the ball only travels for what, 0.4 seconds or something, wasn't it, something like that? Right, so we could do that real quick. So if we just go to the graph screen and go to our parametric, no, not parametric. This would be an actual. This would just be a regular function. So, oops. The right button. Okay, so the speed. So I need the square root. And then it would be 150 squared plus, and then parentheses, what was it, negative 32, and I got to use an x since I'm graphing here, squared. So wouldn't it be that right there? That would be our speed graph, and then we hit enter, and I don't see anything. That's because I don't really have a good window here, so let me go to the window. And so x is actually my t in this problem, right, is the time. So probably plot it from 0 to point, I don't know, 6 maybe, right, because that's the time the ball was, didn't we find 0.403 or something is when it crossed the plate, right? So give it a little time to go on past the plate. And then what would be a reasonable y here? Would be a reasonable y minimum. Well, what is y here? What's y? The height of the ball, right? So what would be the minimum height of the ball? 0. What would be the maximum height of the ball? Oh, wait, no, I take it back. Sorry, my fault. Y is not the height of the ball here, right? I'm confusing my numbers here, right? And it, just like we've been talking about, you gotta think about what it is that what equation you're working with, what it represents. And when I said y, I automatically thought of this right here. No, on my graph screen, what's my y? Speed, right? I'm graphing this equation right here. My input, my x is my time, and my output, my y, is the speed. And what did we have for the speed when it crossed the plate? What was the speed when it crossed the plate? Remember that yesterday? 150.55 something, right? Because it was funny because it started at 150 and actually got a little faster because it dropped. Okay, so let me back up. So do I really want 0 as my minimum speed? Probably not. Probably what? 150, right? Because and actually just so I see a little more of it, let me go about 148. And then maybe 151, because the speed is staying right about 150, but getting a little faster, so maybe something like that, right? So does that seem reasonable then for what the speed is doing? It's going up, right? The speed's going up. It starts at 150, and as it drops, it's getting a little faster, so the speed graph's going up. So in 17C it says, how does a graph shape reflect the physical situation? It's getting faster because gravity's pulling it down. Okay. that's 17C. Okay, good question. What else? Besides 20, anything? Had a few people this morning asking me about 14. You know, where it says eliminate the variable in part B, that's where you just, to just make sure everybody's on the right page there, you got x equals 2t, and you got y equals 3t plus 4. So how do we eliminate the parameter? I'm sorry, not variable, parameter. We want to solve this one for t, so we get t equals 1/2 x, and then plug that into there. So you have y equals maybe 3/2 x, I guess, plus 4, and that would be so that would be the path, that would be the graph. That's what this picture would look like, and but you were just supposed to graph that. So make sure you can do that in the first couple problems. You're supposed to be able to graph it, draw a sketch. Some of your papers I didn't, the sketches were a little sketchy. Right, I mean, you gotta be able to draw a sketch, direction to travel, mark points on it, be able to set your window, make sure you can do all that with your calculator, right? Okay, number 20, let's go to number 20. So this is, again, we need to be able to, you know, we need to know these formulas, right? Oh, the other one, and on 14C, then people were asking about that too. It says, find the slope at t of this parametric curve. So right away, you should think of this. If you're dealing with a parametric function, it asks you about slope right here, y prime over x prime, right? Y prime over x prime. So y prime on that, so what was our equation? It was this right here. So what's y prime? 3. What's x prime? 2. And then it says, why doesn't the answer depend on t? In other words, why isn't there a different slope at different t values? Because it's a line. Yeah, it's a line. It's not going to have different slopes. It's going to have a slope of 3/2, which sure enough, when we did this, when we eliminated the parameter, we found the actual regular equation of the path, sure enough, it's got a slope of 3/2, right? But from here, we could get that as well. The slope formula, y prime over x prime, right? So that's why it said, it doesn't depend on t. The t's dropped out when you did the derivative. All right. So number 20. Well, I don't know. I don't want to spend a bunch of time just redoing this on your calculator. So I'm not sure what the difficulty. I mean, I'm sure there was a varying amount of difficulty or different things you were confused by, or maybe I don't know, just didn't. Know where to go, but they gave you this as the x equation, and then of course the y equation was the same one we've been working with. So they give you this, okay, and so like I said, if I just give you a parametric equation, be able to graph it and be able to work with all of these different formulas, okay, be able to work with all these different formulas on, okay, so be able to do the derivative of each one, that's your velocity, be able to do this formula, which is a speed. And if you need slope, you can do slope. So if we look at these questions on 20, okay, so how much time does the air drag, what time does it cross the plate? So how did we do that yesterday? How did we find out when it crossed the plate? We put a what right here for x? 60.5, right? 60.5 is how far horizontally it's got to travel across the plate. So we put a 60.5 right there, and we solved it on our calculators, right? And we get a t value. Now, you guys don't have answers in the back, so let's look those up here real quick. So it says here that it takes 0.44225, right? A little longer, right? Makes sense to be a little longer? Wind resistance, air resistance, friction, right? So it takes a little longer, okay? So that's the same thing we did yesterday in that problem. How much longer does it take to reach the plate than the dragless ball? So just take that number minus the one we found yesterday, the 0.403 number, right? B, at what height does it cross the plate? So then what? Put that time into the y equation, right? And it crosses the plate at 3.8706 feet. Now, yesterday it was 4 something, I think, wasn't it? was like 4.5 or something like that. Yeah. So yeah, but the one we did yesterday when we said how high did it cross, I think we got 4 something. Well, it's lower, right? Because it's slowed down. The wind slowed, the air slowed it down, and so it's going to drop more, and so it's there. So it's definitely a strike, right? It is a strike then. At what speed does it cross the plate? Well, that's when you just do x prime and plug that number in, square it, y prime, plug that number in, square it, right? And you get the speed. According to this, it came out to be about 125.9. Now that makes a little more sense, doesn't it? It's slowed down. It's not going faster than when we released it, right? So just using these formulas. And then where does it land? We didn't do that yesterday, but we talked about it. What would you do to see where this lands? Put a 0 in here for y, because y is the height of the ball. So when it lands, the y value should be 0. Solve that for t, but that would be when it lands. You want to know where's it land. So then put that t back into this one, and that would tell you where. Right? So, yeah. So hopefully as you hear us talk about that, you say, oh, yeah, okay. That isn't as hard as I was making. Right? Because here's the equation, x for the horizontal, y for the vertical, and then it just asks you these questions about where you're either going to be solving one of these equations set equal to something, or you're going to be plugging something into one of those equations, just depending what you're going to do, or you're going to use the formula like the speed formula then. Okay? All right, so that was number 20, and then they got an answer of 86.851 feet. 86.851 feet is what it says here. Okay. All right. Well, let's move along. We will come back and review this parametric stuff before our next quiz. Because we've got some other things to do here, and the quiz is going to be over sections 3, 4, and 5. That was section 4. So now we're going to go to section 3. And section 3, I don't want to prejudge this or have you prejudge this, but the difficulty in this section is the setting up of the problems. For example, the one we just did, what I thought was nice about number 20 is they just gave you the 2 equations. We have to set up anything; they just gave it to you, and you just have to use those formulas. But this section we're about to do right now is think back to the first couple days, and we did. Remember the snowmobilers stuck in the snow problem? There's a guy hiker stuck in the snow, and we had to figure out what route he should take to get back to the gas station or whatever, right? And we had to set up, right? It was hard. I mean, it was hard. I remember a lot of people came in with questions that you didn't know what to do, how to set that up, right? And it goes back to algebra 2. So what's hard about these problems is very little of the calculus is not that hard. I mean, there's some things you got to do, obviously, in the calculus part of it too. But what's typically hard in these problems is they're typically kind of story problems. You usually got to draw some sort of picture, and you've got to set up an equation. Okay, now some of them, it's pretty much set up for you, so those problems are easier because then you can just focus on the calculus. And then some of them are harder because you have to set up the equations. Okay, so we will be practicing over a number of days here how to do that, and you'll start to see some similarities. A lot of problems involve right triangles, maybe, or we'll get into volumes of cylinders or volumes of boxes or areas or those kind of formulas. So sometimes some of the problems are easier to set up than others. But once we have them set up, then we kind of always do the same thing. And so what this is about is called optimization. Now, optimization is just a fancy name for global max min. Optimization means in this problem, what's the optimum solution? So if we're talking about profit, the optimum would be what? The maximum, right? The maximum. If you're talking about, in a business example, if you're talking about your expenses, your cost, then the optimum would be a minimum, right? The guy's stranded in the snow. We set up an equation for the time it would take him to get there. Well, he would be interested in what? the minimum amount of time to get to the gas station, right? So optimization is just using one word to mean two, kind of like extrema is one word that means either max or min, right? So we talk about optimization, that's what we're talking about, optimization problems. Well, we've already done global max min, really. So what we need to do is we just need to kind of, fine tune what we already know about global max min. The global max min problems we've done up till now have just been with functions. I just give you an f function and say find the global max min. And now we're going to do it as kind of story problems, as real life applications. Okay, so let's review what we should already know about global max min. So here's a function, right? It goes from point A to point B here. Where are the different places that the max, the high point, could be? It could be at an endpoint. Now, in this particular problem, it's where? At the local max, which what's happening right there at that local max? The derivative is 0. So remember our list of candidates, right? So one possible place would be where the derivative is 0, right? In this particular case, that is where the max is, right? Now, in this particular problem, where's the minimum? The global or absolute minimum. It's down here where the derivative, now that's a local minimum, that's still a local minimum, but that's where the derivative is undefined. Okay? Now remember, derivative 0 is called a stationary point, right? And these two together is called what? No. What does that stand for? Critical point. Critical point. Critical points are those two together. A critical point is where the derivative is 0 or the derivative is undefined, one or the other. Okay? A stationary point is just wherever the derivative is 0. So sometimes we say candidates would be at critical points, but I usually like to say those separately, right? I usually say I have two candidates there. One is where the derivative is 0, another is where the derivative is undefined, because I have to do two different things to find those. Okay? All right? So, and then where's the other place? Somebody said it, where the highest point could be. Right? I mean, the graph could have looked like this, right? So now the highest point would be at an endpoint. So the other place to check was that. And those were our candidates. And I always like to say we have 3. We have 3 sets of places we have to look. Right? Now, some people might say that's 4, because there's 2 endpoints, right? Or some people might say that's just 2, endpoints and critical points. You know what I mean? So it's kind of, I usually say it's 3. We have to check derivative 0, derivative undefined, and endpoints. That's how I usually think about it. Okay? Now, some problems don't have endpoints, right? Some problems in the problem don't have an endpoint. And in the story problems, that's sometimes the hardest part to figure out, is what are the endpoints. They don't give them to you. You know, so far in the problems we've done, we're going to do it here in a minute. This is what our global max min problems would look like in the past. Right there. I just give you a function. I give you a set of endpoints. I say find the global max and min between them. And we're going to do that problem just to review how we do it. But the problems we actually do are going to be spending our time on are not quite that simple, right? We're going to have to come up with the thing we're trying to maximize or minimize, okay? And decide if they're endpoints or not. All right. So that's what we're doing. That's what we're doing. So to find our global max min, then we have to go through this process. So whatever we're trying to maximize or minimize, I'll use the word optimize a lot. Whatever we're trying to optimize, we need to have an equation for it. And then we need to set the derivative equal to 0. We need to see if the derivative is ever undefined. We have to see what our endpoints are. And then what do we do with that list of candidates? Put them back into where? The original function, the thing we're trying to maximize. Because what we're saying is those are the only places the max can be. And then to tell if it's a max or min, we just plug it back into that original. Like we have a profit. We're trying to find a max profit. We need to write a profit equation. Do the derivative, so that'd be like P prime maybe. See if it's 0, see if it's undefined, see what the endpoints are. Then we plug those values back into the profit equation and see the different profits. And whichever one's the biggest, that's the one we want, right? That's how this works. That's how this works. Okay, so I have made a list here. I'm not a big fan of just memorizing, do this, do this, do this. However, in this case, it doesn't seem to be a bad thing to do. So I'm gonna write this down. If you ever get stuck on a problem, then this is always something you can kind of fall back on, is kind of these list of steps or whatever. Okay, so first step, identify the quantity you're trying to optimize. So you read a story problem, you've got to identify. So in that hiker problem, you would have to identify time, right? In that problem, it said let X be this or let R be this, and find an expression T that represents the time the hiker is in the woods or whatever. Well, these problems aren't going to say that. These problems are going to say a hiker is, there's a gas station 6 miles from his position. He's 3 miles south of the road. What route should he take to get to the gas station? He can walk this fast in the snow. He can walk this fast on the road. What route should he take to get there the fastest? That's all it'll say, right? So what you have to say to yourself is, okay, what are we trying to maximize or minimize? Oh, we're trying to minimize time. To get to the fastest, we're trying to minimize time. So what I need to do is set up an equation for time. If it's a business problem, it says how many calculus books should we make to maximize our profit? So I identify the quantity. Oh, okay, I'm maximizing profit. So I need to set up a profit equation. Actually, I think I've jumped to number 2. So we identify what it is. So sometimes it's really easy because it just says find the max profit. Oh, well, they just told you what you're trying to maximize, right? So number 2 is, so number 1 is you've identified what it is you're trying to optimize. Now write an equation of that. So if you're trying to maximize profit, write a profit equation. Trying to minimize time, write a time equation. Trying to minimize cost, write a cost equation. Trying to maximize volume, write a volume equation. Okay? So V equals, P equals, T equals. Use those letters maybe. Whatever it is you're trying to maximize or minimize. Cost, C equals. Now, that's typically called your primary equation. I think the book calls it your objective function. Whatever. That doesn't really matter, but if you hear that term, you should know. But that's the thing you're trying to maximize or minimize. That's like your f of x in the example we were just showing a minute ago. That's the thing we're trying to find the max of. Okay? All right. So sometimes those 2 steps are the hardest. Well, step 2 is sometimes the hardest part, right? And sometimes it's just given to you. So sometimes that part's easy, right? But sometimes finding that is the tough part. Okay? Now, sometimes when you write that equation, you have more than one variable. When I give you a function, it says f of x, and it's just got one variable in it, x. But if we've got a profit equation, maybe it's got multiple things in it, or if it's a volume. This would be an easy example. Say it's a volume of a box. So we've got length and width and height, right? The volume of a box is length times width times height. Well, we can't do a derivative with 3 variables. We've got to have just one variable. So it says get that equation in terms of a single variable using other information. These are called your constraints or your secondary equations. So like if we were trying to maximize the area of a rectangular pen to keep our cows in, right? And we want to know what shape should we make it to get the max area. Well, we might have a constraint in there that we only have 100 feet of fence. We have 100 feet of fence available. So what should we do to make the max area, right? So that would be a constraint or something that would allow us to do that. Because what would that mean? Well, because what we'd have is we'd have area would be length times width. That's what we're trying to maximize. But we have 100 feet of fence, single strand electric wire. That's what we're going to do. Okay, 100 feet. Well, what's that? What would be the equation that would, making a rectangle like this, that would use up 100 feet of wire? Nah, it wouldn't be bait. No, it's just 2-dimensional. Length times width is area. It's a perimeter, right? It's a perimeter. It'd be a perimeter thing. So 2L, so what we would know is 2L plus 2W would have to equal 100. Now what could we do with that information? to get this down to just one variable. Just like we did on eliminating the parameter right here before. Solve this for, say, L. So 2L would equal 100 minus 2W. L would equal 50 minus W. Then I could take that and put that in for L, and now I would have area equals 50 minus W times W, so area would equal 50W minus W squared. Now I have an equation for the area, and it's down to just one variable. See what I mean? That's the kind of stuff we're talking about there. Okay? So, sorry, Brianna, I didn't write that on the screen. All right. Just rewind it and replay it. All right. So now, so that's how we can do that, right? That's how we can get that. So eventually it took all of that work then to get down to the type of problem that we've done, right? Now we have a equation that we can now do the max of, right? We're going to do the max. So here's where now our candidates will come in, which we'll see in a minute. Now, while we're on this, what about endpoints? What about endpoints? Now, your endpoints in a typical problem are your x and your x's, right? In a normal function, it's your smallest x and your biggest x. Well, here, our input is w, so your endpoints would be your smallest w. So what's the smallest width we could have? What's the smallest width? Well, yeah, that's right. I mean, 1. Well, what about 0.1? Right? Actually, what we'll do is, usually what we'll do is go ahead and say 0. But you're right. What happens if the width is 0? Yeah, nothing will fit in there. Well, your area will be 0, which clearly will not be a max, right? So what I usually say in a situation like this is, let's go ahead and use 0 as our minimum, even though you're right, then you don't even have a picture. And that happens a lot with endpoints. A lot of times, these real-life situations, the endpoints are not an issue. But from a calculus perspective, on the AP test, all that stuff, you've got to show that you're checking those, right? You've got to show that you're checking all your candidates. Okay, but the one that might be a factor is what's the biggest? Now, in this one, it turns out not to be, but what's the biggest W could be? Not 100. Remember, you have 100 feet of wire. So W could be 50, right? The biggest it could be is if you used all the wire for W. Here, you're not using any of it for W. And the biggest it can be is 50. But then again, if you use it all for there, then you don't have anything for L, and there's no area there either. Okay? So, did you guys go? All right. So, anyway, that would be how you can set up your endpoints, right? So, now, as we know, that when we plug those in, I mean, plug a 0 in, you're going to get 0. Plug a 50 in, you're going to get 0 also. So, those will not be maximums, right? So, you do your derivative and on you go. But that's just a simple example of what one might look like. Okay, step 4. Well, okay, so now once we get to step 3, once we're done with step 3, now the rest of it's just like what we know how to do. This is what we've already done with global max and min, right? Find the critical point. So that means see where the derivative is 0, see where the derivative is undefined. Okay? Identify the endpoints. Now, maybe you'd already done that, or maybe you do it down here. And now, notice it says endpoints or in behavior, because sometimes there are no endpoints. It could go like to infinity. Well, we can talk about plugging in an infinity. Now, you really don't plug in infinity, but you can say, what does the profit do as the endpoint goes to infinity, or the x goes to infinity, or what is the whatever. And then you can tell if it's a max or min, that kind of thing. Okay? So, next step, use your list of candidates. So you got your derivative 0, derivative undefined, your endpoints. So if you've got a list of those, you plug them back into the original, and that's your justification. Now, notice I said number line, or some justification, because most of the time it's a list of candidates. But what happens if you only have, what if there are no endpoints? And what if you only have one candidate? Why can't you do a list of candidates with only one candidate? It's not a list. Well, yeah, it's a list with one thing in it. Why can't you do a list of candidates with only one candidate? You can't compare it. That's the whole point of a list of candidates. You plug them into the original, you see which one's the biggest, you see which one's the littlest. If you don't have anything to compare it to, you can't tell if it's the biggest or the littlest. So that's where you could do a number line. You could do a number line of F prime or P prime or A prime or whatever, and you could see if it goes from positive to negative, then what do you got? Number line goes from positive to negative, you got a max. And since that's the only candidate, it can't ever go back up again, right? It goes positive and then negative. It's increasing then decreasing, so you got to have a max. So that's why it says a number line or some justification, right? So in some problems, you have to think that way, okay? But most of the time, it's just going to be like we've done, list of candidates. And then answer the question using appropriate units. Since these are story problems, it may say how many books should you manufacture to get the max profit. It might be what is the max profit? You know, I mean, so you got to answer the question. Got to answer the question. All right? So that's kind of the steps that are involved. That, you know, I always never know for sure. Should we go through the steps before we've done some problems, or should we do some problems and then come up with steps, whatever. All right, let's go through this problem right here. So we can just review with ourselves here how to go through the process. So the question here is find the global max and global min of this function. So in our steps there, we're already down to step 4. We already have the equation, the primary equation. We already have the thing we're trying to maximize or minimize, which is f. And we've already done step 6 or 5, whichever. Doesn't matter, but the one that said identify the endpoints. They're already there. They were just given to you, right? So this is kind of the easiest of all problems when you have this information. So all that's left is to do what? Which is the derivative is 0 or the derivative is undefined. So we do the derivative, right? So the 1 disappears, we get 6x squared minus 4x cubed, and we do what with that? That'd be for the stationary points, right? Let's find when the derivative is 0. Let's find when the derivative is 0. So we do that. So to solve that, we're going, now, I'm trying to think. On this particular quiz, this is I can't really promise one way or the other. If there's going to be a calculator part and a no calculator, definitely be a calculator part like for those parametric equations. Probably be calculator for everything. But even if this is a calculator problem, you're going to do most of the same stuff. You still have to write all this out. Now, you could go solve this on your calculator right now. That'd be fine. Or maybe you just want to factor out a what?
2x squared.
2x squared, right? Which would give you 3 minus 2x. So either x equals 0, or what would this one be? 3 minus 2x equals 0, so 3 equals 2x. So 3 halves. Yeah, be careful, and that's a problem. Sometimes a lot of people do that in their head and they get 2/3, or negative 2/3, or negative 3 halves, or whatever. So show it if you need to, or go to your calculator and have your calculator do it. So we got 2 stationary points, right? So your calculator could have solved that, but make sure you write it on your paper. But then the work may not need to be there. You could use a calculator to do it. All right, so we got those 2. They're both inside of our endpoints, so that's good, right? If we got something that was outside of our endpoints, we would have eliminated them. Okay, what's next?
Plug it in.
List of candidates. Plug them in, right? So I come over here, so I'm going to do f of -1. I'm going to do f of 0. I'm going to do f of 3 halves. I'm going to do f of 2, right? Somebody got their calculators handy. We can help out here a little bit. Do the 3 halves one for sure. The other ones we can do pretty easily probably. So 0, that's easy. That'll be 1. Put a -1 in there. That'd be -1. That'd be -2. -1 to the 4th would be 1. So 1 minus 2 is -1 minus 1. That's -2, I think. 2 would be 8 times 2 is 16. 2 to the 4th is 16. 1 plus 16 minus 16, that'd just be 1. What about 3 halves?
Two, 1, 6, 8, 7, 5.
Okay, so 2.688. You guys agree with that? Anybody else getting that? Okay. So, and then how, depending how the problem was worded, but if the problem said find the, global max and global min, then max is 2.688 and the min is -2, right? And then we'd have, right? Your list of candidates is your justification, right? There you go. So that is a basic, that is just a very basic, and there's not going to be any of those on the quiz, right? The quiz is one of these is more going to be story problems, but that takes you through the process. Once you get the equation you're trying to maximize or minimize. So this is what I'm talking about when I say it's not the calculus that throws us off as much, right? Because there's no calculus here until you get to this step, right? Until, if you look back here, there's no calculus until you get right here. And right here. Really, steps 4 and 6, those are the only calculus steps. We do the derivative. See, and I forgot one other thing. I should write here, f prime never, we want to get in a habit here, f prime never undefined. So that shows that I checked everything. I've got my endpoints, I've got where the derivative is 0, and I also checked to see if f prime is undefined. But f prime is just a cubic, that's never undefined. What are you looking for undefined? Divide by 0, maybe negative in a square root, but usually if there's a square root, then there's not, you couldn't have a negative in the original either, so that's usually not an issue. So most of the time it's 0 in the denominator is typically what you're looking for there for the undefined. Okay, let's do this one. Find the global max and min of this function. Now how is this different than what we just did? There's no endpoints, is it? Okay, but that's okay. Let's do it anyway. So global max and min of this function. So where do we start? Find the derivative. Okay, do it real quick. Do the derivative. Do the derivative. Don't look up here now. You're right. You have your calculators to solve that, right? Because this is not one that you would have the option of doing without a calculator, right? That's not a function we could solve. So go ahead and get on your calculator, set that equal to 0 and solve it. Oh yeah. You bet. 0.367. What? Is that it?
0.367.
Oh, okay. So it could be 8, it could be 7. Actually, it doesn't matter on that.
0.374. 4.
Well, the 4 and 9 is not right. Okay. And even if it was a 9, we wouldn't have to round it up, right? 7, if that was an answer we had to give, 3 decimal places would be okay. Now, if we're going to plug that back into the original, and this is important actually because that's what we are going to do, right? We're going to plug it back into the original, possibly. So then you'd want to do more, probably 5 or 6, I think, most of the time, right? Okay, hey, is that it? Just that one?
Yeah.
Okay, that is possible. Okay. So, well, that's what we just talked about a little bit ago. Oh, isn't that lucky? There's only one candidate. We don't have any endpoints. If there are no endpoints given, then we're just talking about the natural domain of this, which would be negative infinity to infinity. Now, it's a 4th degree power, and it's negative, so that means we might have something like this, right? So probably if you already know what this function kind of has to look like, you know what's the minimum going to be. Well, there won't be one, right? Yeah, negative infinity, essentially. But what we would say is no minimum, right? If the direction said find the global max min, then that's what we'd say there is no minimum. There is no minimum, right? All right. Now, what I did skip here a little bit in your book, so I should clarify here a little bit when we talk about no minimum, because if you go to page page 234 at the bottom, and it says something called the extreme value theorem, which is something we're going to talk more about later in the chapter. But the extreme value theorem says if f is continuous on a closed interval AB, then f has to achieve both a global max and a global min. Now that doesn't tell us where to look for them. That's our list of candidates. But all it does is says you're guaranteed to have extreme values. But that there has to be two things. It has to be a continuous function, which this is. All polynomials are continuous. It has to be a continuous function, and it has to be on a closed interval. Well, there is no closed interval here. So there doesn't have to be a max and a min, right? But on like this problem, we knew there had to be both a max and a min. Now, by the way, wasn't going to say this before, or I didn't say it before. If this would have came out to be, say, 0.688, what would have been my max? 1, right? The max would have been 1, even though it happens twice. We don't care about that, right? The max would be 1, right? Because it didn't say where is the max, it says what is the max. So if this was 0.688 instead of 2.688, we would have said the max is 1. Kind of like the sine function. What's its global max? 1. Happens a whole bunch of times, but the max is 1. It's the highest value. All right, anyway, back to this. So here's where a number line would be a good justification, an f prime number line. So you've got your calculators. So let's put on a 0 here and maybe a 1 here. And well, I guess you wouldn't need your calculator. Those are easy numbers to plug in. And so let's put a 0 into this. So 0, 0, that'd be a positive. Now remember, we're plugging this into f prime. So this is the thing that sometimes confuses people. Normally on a global max min problem, you're plugging back into the original function because you're looking to find what those values are that are high or low. But a number line is f prime, because we're trying to see when the graph's going up and when it's going down. That's what we're looking for. Okay, so I plug a 1 into here. I'd have 1 minus 3 minus 12, which is negative 14. So this graph doesn't have multiple humps like this. This graph actually just goes up and then goes down, right? Because this is what this number line tells us right here. It's only got one stationary point. I already wrote this over here. The derivative's never undefined because it's a polynomial, and polynomials are never undefined. So I wrote that down. We found where prime 0. It's only one place, so you only have one candidate. So here's what you would put then as your answer. Now, let's say the directions were find any global max or min value. Well, you would say no minimum. Okay? What would you say for the max? Would you say 0.367? You've got to plug that into the original. Let's do it. Because if it asks for the max or min values of the function, they mean the outputs of the function. That didn't say where the max was. Okay? That's where it is at 0.367. Okay? So take several of those decimal places. So put 0.36749 whatever and plug that back into the original. You know, you've got on your screen already when you solved it, probably x equals that whole number. So the good thing to do is just type in x minus, because you can do this a lot, aren't you, when you do your list of candidates. So just type in x minus x cubed minus 3x4 vertical bar, and then go up and grab that x equals. I mean, that'd be a good way to do it, but whatever. Anybody getting it yet? 263.
Yeah.
Okay. So there's our max value. That's the y value at 0.367. So we've got our minimum, we've got our maximum, And then, now the number line by itself is not enough justification though for a global max min. So we would have to say right here, since F is always increasing before 0.367 and always decreasing after we have a global max. So you'll hear me talk about that in these situations where we can't do a list of candidates. And the AP, they've actually said for their test, in an acceptable justification of a global max or min, the key is the word always there. The key is the word always. Because you can't just say it's increasing before and decreasing after. That just means a local max, right? It's always increasing and always decreasing after, which means there's that only one, right? There's only that one candidate. So that's the key. All right?
So like what if it's like that one?
This one?
Yeah.
Well, then what would have happened is you've got three places where the derivative would be zero. So we'd have had three different
But
numbers.
like if the right top was like higher.
Exactly.
But then
Well,
it's not always increasing.
right. Okay, here's what I'm saying. If it would have looked like this, right?
Yeah.
Now I would not have done a number line. Because I'd have had 1, 2, 3 candidates. Yeah. I'd have had 3 candidates and then I'd have done a list of candidates, right? Yeah, and then I'd have plugged them in and then right. So it's only when we have the situation. See, that's why I was surprised which I shouldn't be surprised because this is my problem. But that's when you said there was only one answer here, right? I had in my mind this situation, so I was ready for more answers. But as soon as it was just one, then I was like, oh, yeah, it's going to be that, which of course is what I meant to when I made this problem. But, oh well, my mind's going on me again. All right, so here's the next one we want to look at. It's called the box problem. You may have seen that picture I had up here on my calculator a minute ago. Okay, and this is just a classic calculus problem when it comes to usually the first optimization problem people deal with is the box problem, and that's you take a piece of paper and you cut out the 4 white corners, and then you fold up the orange pieces and you make a box, right, out of a piece of paper. So the question is, how big of a square should you cut out of the corner to make the box that has the biggest volume? Now, you may have done this in Honors Algebra 2, I don't know, when you were doing parabolas. Because you can do it without any calculus. You can graph. Because setting up the equation, again, setting up the equation doesn't involve any calculus. That's just algebra, right? That's just algebra. So here's the situation. So what we have is you can see a graph and it's kind of interactive. So if I go over here and I cut out littler squares, you can see the volume. There's the box. It doesn't have much volume, even though the base is very large. The height's not very big. It's got a volume of 37. So over here we've got the volume graphed. But if we cut out bigger squares, the volume keeps getting bigger and bigger and bigger and bigger and bigger until a certain point when the volume starts getting smaller and smaller again, right? So somewhere in there is an optimum, and that's what we're looking for. We're looking for that place. Well, in Algebra 2, what you do is you set up the equation, go to your graphing calculator, graph it, look at the parabola, find the vertex, and boom, you got it, right? And so you don't need any calculus to actually find it. But we start with simple ones like that. We'll go and use the calculus to find it, but it just lets us practice our procedures for doing it. But then as you get to more difficult problems, the calculus becomes more important. Okay? Well, anyway, so you can tell there's a place right in there, right about there, where you get the peak of that, and that would be the max. All right? So a manufacturer who, because if you would want to maybe create a shipping package for something that would hold the most for a fixed cost, right? For a fixed set of materials, right? You wouldn't want to use more material and get less volume. That would be inefficient and would affect your profits, right? And so this is what, this could be something that you would be tasked with figuring out. Okay, so let's do this. So let's say that the paper, let's make it easy on ourselves. Let's say it's an 8 by 10 sheet of paper. Instead of 8 by 11 and a half, we'll make things easy on ourselves. And so we're going to draw a picture. So this is the type of problem I'm talking about, is setting it up is the key. So step one was identify what we're trying to optimize. So what are we trying to optimize here? Volume. We're trying to find the max volume. So right away, step two then says find an equation for that quantity. So I'm going to call it V. I don't want to call it f of x every time because it'll mean more to me if I use the letters of what it means. So I need a V equation. Now I can write V of x here if I want, like f of x, but I don't have to. I can just write V because we don't know what our other variables are right now. Okay, well if I cut out these squares, and they are supposed to be squares, okay? Now what do we know about volume of a box? What is the formula for volume of a box? Length times, okay, we're in big trouble. Now, if it is a more kind of confusing kind of a formula, that I may give it to you. You know, if it's a cylinder or things like that, it's not going to be a huge deal to have to memorize these. But I mean, we ought to know a box, right? Length times width times height. So we could go ahead and write that down if we want to. But the problem, like we said earlier, that's 3 variables. We don't want it to be 3 variables. Okay, so let's go to our picture. So again, our steps back here, write and label the equation of that quantity, or I should have probably said draw a picture and label. Probably a picture should be in here somewhere. That's usually part of step 2, right, is a picture in these situations. So what can I do here? How can I label this thing?
Length can be like 10 minus 2x.
Okay, where's your x coming from?
The cut out pieces.
Okay, I think that's a great idea, because what we don't know is how big a piece to cut out, right? So I think calling that x would be a great idea, right? And so the length, she's calling, so let's say this side is 10 up here, and this side is 8 down here. So the length of so here's my actual base or bottom of my box right here, right? So this would be 10 minus 2x. And this side would be 8 minus 2x. So there's my length and my width. And what's my height? When you fold up those pieces, it's x, right? It's the whatever size of square you cut out. So there we go. We just were very quickly able to get all of that. So length is going to be 10 minus 2x. Width is going to be 8 minus 2x. And the height is going to be x. Length times width times height. Now, on your calculators, you can just type that in. It's probably not a bad idea to do that, so we don't have to FOIL it all out. So go ahead and type that in, and let's just let the calculator do that for us. We could do the derivative right now the way it's written, but I don't know. We're just used to seeing it expanded out more. There is an expand command inside the algebra menu. I don't know. Try typing this out. You might need a time sign on that x. I don't think so, since it comes after the parentheses. Does it expand it for you when you type that in and hit enter? Or does it leave it factored?
It expands it a little bit. It's still
Expands it a little, but it's still factored. So here's what I want you to do. Go to the algebra menu. Go to the algebra menu and find the command expand. Yeah, the third one down. And then type in the 10 minus 2x inside of there. And then what's it give you?
4x cubed minus 36x squared plus 80x.
Okay? So that can be a useful one because then, but again, the calculator can do the derivative for us, right? So I could just told it to do the derivative of that the way it was written, but I don't know. I think we're more comfortable with this, probably. But anyway, before we do the derivative, let's think about our steps. So step 1 was identify, so that was volume, and then write an equation in terms of one variable. So we used our picture to help us get it into one variable. And so now we know, so now it's like our normal thing. Oh, what don't we have right now? Actually, that's step 5, but what? 5 and 6, we don't have endpoints. So let's go ahead and do that. Now, here's the key to endpoints. This always seems to throw people off. The key to endpoints is it's your input variable. You got to look at the input variable. Once you have your function established, you look at the input variable, in this case x, and you say what's the smallest it could be and what's the biggest it could be. That's how you do input. Look at your input variable and ask yourself what's the smallest and what's the biggest. So in this picture, what's the smallest x could be? 0. Which, of course, if it's 0, we wouldn't even have a box, and we know that's probably not going to be our maximum, right? But whatever, that's going to be our, that happens quite a bit in these problems. What's the biggest x could be?
4.
Good. 4, right? 4. Because if x is 4, you would use up this whole side. You wouldn't use up this whole side, but you'd use up this whole side, right? X couldn't be 5 because you wouldn't have enough here, right? So the biggest x would be 4. Okay? So that's how we get our inputs. Well, now, if you look at where we're exactly where we were when we did this problem. We have a function, and we have endpoints, and now you just go for the rest of it. Okay, so let's do it quickly. So we do the derivative. It's going to be a polynomial, so b prime is never undefined. Right? Write that down. You'll end up writing that a lot, but it's good to always think about it. So this will be 12x squared minus 72x plus 80. Somebody set that equal to 0 for me real quick. Could probably factor out something. But since we got the calculator, it's not a big deal. So let's solve this. I know I'm going to have a list of candidates because I do have endpoints. So I'm going to have v of 0. I'm going to have v of 4. And I'm going to have v, and well, then we'll see.
So the first one is 1.472.
Okay.
And the next one is 4.527. Oh, 4.528.
Okay. Any thoughts on those two?
Can't use the second one.
The second one is no good because it's outside of our endpoint. Right? So we'll just cross that one off. So we're going to plug in a 1.472. All right, now we kind of already know what's going to happen on these endpoints, right? If I put in, or at least on this one, we put in a 0 back into the original. Now remember, we're going to get 0. We're not even going to have a box. Okay? And I didn't leave myself nearly enough room to write this. Okay, what about a 4? Let's put a 4 back into the, remember, we're putting it back into the V. We're trying to find what is our volume. We want the max volume. I don't think we get 0. Oh, yeah, we will. We have to get 0.
8 minus 2.
Yeah, because this side would be 0. So our width would be 0. Yeah, we should get 0. Yeah, absolutely. Because, right, yeah, the 8 minus 2x is going to be 0. Yeah, duh. Okay. So we get 0 there. And then 1.472, obviously that's going to be our max. Okay, I don't even care. You can plug it in, that's fine, but whatever. We know that's going to be our max. And it's already justified. Right? Geez, we did all that work, we're not even going to find out. The suspense will kill me. Stay up all night. All right, so whatever that volume is, right, that's going to be your max volume. Now, you could do this with a number line. You could make the argument, and you would be correct, I think, in saying those endpoints don't make sense. You can't, it's supposed to be a closed interval. You can't have 0. You can't have 4 because that's no volume, right? So if you wanted to make that argument, then this would become a one-candidate problem, and you could do a number line, right? You could say, 0 and 4, I'm going to say there's no endpoints in this problem, and I'm just going to do this candidate, and what would you get? You'd get the volume going up and then going down, and it'd be just like we did before. You'd say it's always increasing until 1.472, and then it's always decreasing after the volume, so therefore the max volume is up here. So that would be okay to do. I think a lot of people would rather do endpoints, but, then you do your list of candidates. So that's totally up to you. All right, last problem, and then I'm going to let you work it. Okay, so 2 positive numbers. So you have a similar one to this in your homework, and you have a similar one to this box problem. Well, no, this area. There's one with area. Your homework's only about 5 problems, but remember when we did those story problems in the first week of class? There was only about 4, and they were all impossible.
Yeah.
You know what I mean? So you might get that feeling a little bit on it. There's one of them that's really hard. The Shanghai problem is a tough one. okay, of the 5 I've given you. Okay, but that doesn't mean I don't want you to spend a little time thinking about it and trying some things with it. Okay, but don't be afraid to, to like, did he really expect us to be able to just whip this out? It says in the problem, it says it's on the entrance exam for Shanghai University in China or whatever. So if you can't do it, I guess you're not getting in. So cross that off your list of college applications. So anyway, 2 positive numbers add up to 18. What is the max product of the 2 numbers? Okay, so we got 2 numbers that add up to 18. What is the max product of the 2 numbers, right? Like 1 and 17, right? Adds up to 18. What's the product of those? 17, okay? 2 and 16 add up to 18. What's the product of 2 and 16? 32. Oh, that's bigger, right? 3 and 15 add up to 18. 3 times 15 is 45. Oh, that's big, right? I mean, and so you may already know what it's going to be, right? And you could probably just go through the list, which is fine. But that's not what we want to do. We want to practice the process here. That's what we're saying. Okay? So, number 1, identify. What is it you're trying to maximize or minimize? What are you trying to maximize or minimize?
Max product.
Product. So I would write P equals, right? P for product. First step, right? Identify what it is and then write down that letter to start your equation. Because sometimes people get most confused by that. They just don't know what to call it. They don't know what to call the thing they're optimizing, right? So for some reason that gets to be a sticking point for people. So I always emphasize that. All right, so what would that equation be then? So step 2, write an equation.
X plus Y plus 18.
Now it's product. X times Y. So we're going to let X and Y be our 2 numbers. And product is multiply, right? X times Y. Now, what you're getting into is the next step, right? Our helper equations, right? We want to get this down to 1 variable. What other information is here? X plus Y equals 18. That's our secondary equation, our constraint, our helper equation, whatever. So what can we do with that?
Solve for X.
Or Y, well, either one, doesn't matter. So Y would be 18 minus X, and now I can plug that back over into here. So I got X times 18 minus X. Distribute that through or do it on your calculator, whatever. I got 18X minus X squared. Now, yes, we all know that's an upside down parabola, so it's going to have just 1 max, right? It's a pretty simple situation, right? But that's okay. We're just thinking about the process here. Okay, so we've set up the thing we want to maximize. Do we want to talk about endpoints? We could. If X, you got 2 numbers. One of them's X, the other one's Y. What's the littlest one of the numbers can be?
1.
It didn't say they had to be whole numbers, right? So it could be like 0.1, I suppose, but let's say it is whole numbers, okay? So 1. And what's the biggest it could be? 17, right? If the other one's 1, the biggest the one could be is 17. So our endpoints are like 1 and 17, right? And so then the next step is find the critical points, derivatives, set it equal to 0. The derivative is 18 minus 2x. Set that equal to 0. You get x equals 9, right? X equals 9. So if you want to do a list of candidates thing, or if you want to say, hey, the P function, the product function is an upside down parabola. It's only got 1 max, which is at the vertex, which is 9. So in that list of steps, what I said there is do a list of candidates, do a number line, or some justification. So that would be an okay justification. Say, hey, the product equation is an upside down parabola, so we know that it's going to have 1 max at the vertex, which is when the derivative is 0, which is this. So if you just wrote that out, that would be acceptable. But chances of having one quite this simple is probably pretty slim. All right. So anyway, so x equals 9. So our list of candidates would be, right, if we were going to do it this way, if we were going to do our endpoints, product P of 1, P of 17, and P of 9. Right? Well, P of 1, if you put a 1 in here, you get 18 minus 1, which is 17. Put a 17 in here, well, we already know that's going to be 17 also. Right? 17 times 1, 1 times 17. And then put a 9 in there. 9 times 9 is get 81. There's your max. So the max, what is the maximum product? It's 81. Now, Jamie, you raised your hand right away at the beginning of this problem. What were you going to say?
That's the answer.
Yeah, how'd you know that?
Because when you got something like this, it's usually the two numbers that are close together that add up to a total.
The perfect square, yeah. It's just a geometric fact that for a fixed perimeter, the max area, like we were doing that perimeter problem right there, right? For a fixed perimeter, the max area is going to be what? Or the shape with the max area is going to be what? If we were going to fence in our cows, and we wanted to do the max area here, what do you suppose it would be? A square, 25 by 25, is what the answer to this problem would come out to be. That's just a geometric fact. With a fixed perimeter, the shape with the max area is going to be a square. Same thing with a box, right? With a fixed surface area, the max shape is going to be a cube. Now, that didn't happen in our box because why didn't, in the box problem we did, why didn't we get a cube as our answer?
Because our base was a cube.
Well, no, but it could have been. Oh, you mean because of the 8 by 10 that we had. Plus, here's the other reason. Yeah, you're right. It was an 8 by 10 sheet of paper. The other reason is because it was open top, right? If you were going to build a box that had and wanted to do a minimum surface area, then it would be a cube. But we had set the base already on ours as 8 by 10, so we had said that. So there can be some other issues in there, but that's basically what this problem is. Two numbers add up to 18. That's the perimeter part of it. The max product of the two would be like the area part of it. So that's the same thing. So that's why it ends up being the perfect square, the number right in, like he said, in the middle there, the 9 times 9. So that's just a geometric fact. We didn't need calculus to do it, but the process works as we go through. Okay? All right. So your homework then is the 4.3, day 1. Okay? Now, to be honest, they don't get harder as you go along. The Shanghai problem's in the middle. I think the easiest one might be the last two, or the easiest problem might be the last two, possibly. One of the problems is very much like the product one we just did. So you should be able to mimic that a little bit, for sure. The last equation, the last problem on the homework, number 22, has all this stuff about cost, and it's a box shape and that kind of stuff. But it actually is one of the most doable ones on there. It seems really long, and so I know how you guys are. You get to the last problem, you're like, oh my God, there's no way I can get this last one. You know, the last problem's got to be the hardest.
Yeah.
You know what I mean? I think that's what happened to number 20 today. But you know, it's not. It's one of the most doable ones, probably, that would fit, you know, with what's going on. So.